Hi, George Diamond here. Now today in my calculus class we'll be starting a new unit, right? So we use the Larson text, and so for the first part of this semester, first part of the year, we've been mainly working with derivatives. Okay, now we're starting chapter 4. Now chapter 4 involves integration. Now the first thing we're going to look at involving integration, this is in our textbook, this is section 4.1. We're going to start off with antiderivatives and indefinite integration. Now this is video number 1. Now video number 1, we're going to be, I'm just going to run through some information on my PowerPoint here. Talking about antiderivatives and indefinite integration, defining them. Now what you're not going to see on this video is a bunch of examples. Now that'll be in video number 2. So if you want to see a bunch of examples, some trigonometric examples and stuff like this, how to find the antiderivative, then you want to take a look at my second video. But this video here, we're not going to see a lot of examples, just a couple real simple stuff that we'll look at here on my PowerPoint. But let's get started. Now, so everybody in my class, they're familiar with derivatives. They know how to find the derivative pretty well, I think. So let's take a look at a little introduction to antiderivatives. So think about this now. Okay, now let's take a look at, I've got two charts here. On the left, I'm going to bring up the derivative. And on the right, I'm going to list what my students would think of as the original function. Right? So think about this now. Here's a derivative. Say the derivative f prime x equals 3x to the second power. Now I want you to think of, what if this is the derivative, what would the original function have been? Now, most of my students, all of my students know that the derivative of x to the third power is 3x squared. You multiply your exponent, then subtract 1 from your exponent. Right, so if this is the derivative, 3x to the second, most of my students would tell me that the original function is x to the third power. Okay, let's look at another one. If the derivative is 2x, okay, what would the original function need to have been? And most of my students would indicate x to the second power, because they know the derivative of x squared is 2x. Right, so if this is the derivative, then that would have been the original function. Okay, what about a little expression like this here? Let's say the derivative of 4x to the third plus 2x minus 8. Now think of the original function now. The antiderivative of 4x to the third would have been 4x to the fourth power. The derivative of 2x would be x to the second power, right? And the derivative of minus 8 would have been minus 8x. So when you take the derivative, you drop the variable, right? So most of my students would have indicated that the original function would have been this right here. X to the fourth plus 8x squared minus 8x. Okay, what about a trig function? What if they've given that the derivative of a function is cosine x? Okay, what would you imagine the original function to be? Now, if you remember, the derivative of sine x is cosine x, so if this is the derivative, then the original function would have been sine x. Right, so this is what my students would have indicated. So think about this now. It says that, so as we're looking at antiderivatives here, the function capital F of x is an antiderivative of f prime of x. Right? So when we're talking about antiderivatives, capital F of x, okay, represents the antiderivative of a function, of a particular function. So this is the official definition. So let's go ahead and take a look at it. It says, so if you had to define, look at the official definition of antiderivatives. Okay, this is a function f. This capital F is an antiderivative of f on an interval I, okay, if the derivative of capital F of x equals f of x. Right? So the derivative equals f of x. This describes the antiderivative. Right? Now a little note. We said that capital F is called an antiderivative of f rather than the antiderivative of f. Now that's important because I'm going to show you why that's important here in just a second. Now keep in mind, we're saying when we talk about the antiderivatives, f is called an antiderivative rather than the antiderivative. So take a look at these three functions up here at the top of my PowerPoint. We got x to the third power, x to the third power minus 5, and x to the third power plus 3. Now, if you look at all three of these functions, if you take the derivative of each one of those, the derivative of each one of these functions is all the same derivative. The derivative of x cubed is 3x squared. Well, the derivative of x cubed minus 5, the derivative of x cubed is 3x squared 3x squared, and the derivative of 5 is 0. So these first two have the same derivative. Same thing with the last one here. The derivative of x cubed plus 3. The derivative of 3 is 0, and the derivative of x cubed is 3x squared. All three of them have the same derivative. Right? They're all different functions, but they all have the same derivative. So, so you think about, so these are all antiderivatives of 3x to the second power. All right. Now, if f of x equals 3x to the second power, this is how we compensate for this. All right. So the fact that these are all have the same antiderivatives. So when you find an antiderivative, you're actually finding an expression that represents an entire family of antiderivatives, if you will. All of them having a different y-intercept. So this one has a y-intercept of -5. This one has the last one down here on the end, the plus 3, has a y-intercept of plus 3. So they'll have a different y-intercept. So really when you find an antiderivative, you're finding an expression that represents the entire family of antiderivatives. So if you're asked to find the antiderivative of 3x to the second power, there's actually an infinite number of antiderivatives, all of them with different y-intercepts. So to compensate for that, we say the antiderivative of 3x to the second power is capital F of x equals x to the third power plus c. So the plus c is called the constant of integration. We've got to put that plus c on there to compensate for the number on the end, the y-intercept. Because when you take the derivative of that number on the end, it gives you 0. So when you find the antiderivative, in this case would be x to the third power plus any particular number. Right? So when we ask for the antiderivative, we say this is an expression, if you will, for the antiderivative, x to the third power plus c. So a very common mistake is that students forget to add the plus c on the end when you're looking for the antiderivative. But like I said, this indicates an entire family of functions. So note, but this is a little note here on my PowerPoint. Okay, the family of functions represented by capital F of x is called the general antiderivative of f. This is called the general antiderivative. Now, to get a particular antiderivative, we're talking about just one of those functions. This is called a general antiderivative of f. Now, if you look at the graph of these, like I said, the difference here is basically just they cross the y-axis at different locations. Here's the three that we just looked at here. So you can see y equals x to the third power. This is a cubic polynomial. Across the y-axis at 0. Y equals x to the third minus 3, cross the y-axis at -3. X cubed plus 5, cross the y-axis at plus 5 up here. Now, notice, as you look at each of these graphs here, if you pick out a particular point on any particular curve here, so let's say right here, if you draw your tangent line here, or here, or here, okay, the tangent line to the curve is all going to be the same on each one of these functions. All right, so keep in mind, this is just 3 of the antiderivatives. There's an infinite number of antiderivatives. You can imagine this same curve crossing the y-axis at positive 100, right, at positive 1,000 even. So there's an infinite number of antiderivatives. So when you're getting the antiderivative, you're getting an expression that represents the entire family of antiderivatives. All right. Now, some notations for antiderivatives here. And this is given the differential equation. Now, differential equation is simply an equation with a derivative. We'll define it in our next video. But if you have dy over dx equals f of x. Now, keep in mind that we looked at this when my classes, we kind of looked at this when we're looking at derivatives. Okay, dy over dx does not mean dy divided by dx. But sometimes it's convenient to kind of think of it as division, as a fraction. So typically with differential equation here, it's convenient to rewrite this as dy equals f of x times dx. So you can kind of treat it like it's a division and multiply dx to both sides. Even though it's not really division, sometimes it's convenient to rewrite it like that. Okay, now the operation of finding all the solutions is called antidifferentiation or indefinite integration. So the process of finding that function plus c, okay, that process is called antidifferentiation to get the antiderivative, or what we call indefinite integration. All right. Now later on, my classes, and you'll see the video on this later, we'll be looking at something called a definite integral. What's called a definite integral. Now, a definite integral is a little bit different here, right? So you still got to find the antiderivative, but a definite integration involves, as you can imagine, a curve. Let's see if I can sketch this right here. So a curve from, say, A to B. Now, definite integration involves finding the area between the curve and the x-axis, or what we call the area under the curve. So definite integration is area under a curve, whereas indefinite integration, you're just finding the actual expression for the family of functions. So definite integration involves finding the antiderivative. That's your first step, basically. Then after that, there's some other stuff you have to do. But this is indefinite integration, whereas definite integration involves area under a curve. All right, now we'll be looking at that later. But the actual operation is called antidifferentiation or indefinite integration. All right, denoted by this expression right here. This here is called the integral symbol. So the antiderivative of f of x dx is equal to capital F of x plus c. So you're going to find your antiderivative, what would have been the original function if you were finding the derivative, right? Okay, plus c. Now, a couple parts here when you look at an integration equation or expression here. Okay, first of all, the antiderivative of f of x here, f of x is called the integrand, right? Now, dx is called the variable of integration. So in this case here, you're integrating with respect to x. But you're not always going to integrate with respect to x. It may be a different variable. It could be time, or it could be some other variable. And we said the plus c down here at the end that you're always going to add. So never forget to add the plus c at the end. Okay, this is referred to as the constant of integration. So remember your three parts. Okay, first you have your integration symbol here. Looks like a little wavy line, kind of. Just a little wavy, like a little wavy line. Okay, the expression being integrated, this is called the integrand. You got your variable of integration, and then the plus c on the end. Whenever you find your antiderivative and you do the plus c, that's called the constant of integration. Now, some basic integration rules. Now, if you remember with the derivatives, there were four major rules for derivatives. Remember, we had the general power rule, we had the product rule, quotient rule, chain rule. So we had four major rules for derivatives. We don't have those for antiderivatives. Now, these are just a couple of basic rules here. Now, a little note here that integration is the inverse of differentiation. So these are inverse operations. So when you're taking the antiderivative, once again, this is the inverse operation. So let's take a look at our first rule. Rule number one is our basic rule. The antiderivative of 0 is c. It's just c. So the c could be any number. So the antiderivative of 0 is c. Second rule. Now once again, the second rule. The antiderivative of k. Now k is a number, right? Is k times x plus c. So let me show you an example. I got a little example on the PowerPoint here. This is a real simple rule, but it's important that you remember this rule when you find the antiderivative of a number. So say, for instance, a little example, the antiderivative of 3 with respect to x. So the antiderivative of 3 dx is 3x plus c. So remember now, if you were taking the derivative of 3x, would give you 3. So the antiderivative of 3, you add the variable plus your constant of integration. So the antiderivative of 3 would be 3x plus c. So that would represent the family of integrals. So remember, when you're finding the antiderivative of a number, all you do is add a variable. So add your variable. Another rule, what's called, I guess, I refer to this as a constant multiple rule, I guess, where you have k is a constant being multiplied to your function. And you can actually pull that constant out in front of your integral and multiply. So this is actually equivalent to k times the integral f of x dx. So if f of x is your function times some number, you can pull that number out of your integral. Kind of gets it out of the way, then you can multiply it at the end. So for instance, here's an example. If we have the integral f of x, the antiderivative of 6x squared dx, right? So this is our integral. 6 would be the constant multiple. So what you can do is you can actually pull that 6 off. You can put it out in front of your integral, and then you're just simply finding the antiderivative of x to the second power. And then you would simply multiply whatever you get times 6. Now, I'm not going to do that. I just want to illustrate the example. Now, this brings us to rule number 4. Now, this is the big one. So remember I said that when you look at the rules for derivatives, there's 4 major rules. This one really you only have one big rule. You get these little bitty rules, and then we have the power rule for antiderivatives. So what's called the power rule. Now, the power rule goes like this. If you're finding the antiderivative of x to the n power dx. Now, if you remember the rule for derivatives now, if you're finding the derivative of x to the n, you would multiply and then multiply the exponent to x to the n, and then subtract 1 from your exponent. Well, antidifferentiation, you do the opposite. Okay, we're going to add 1 to the exponent divided by the exponent plus 1. So this rule goes like this. X to the n plus 1 divided by n plus 1. Right? So this is called the general power rule. Now I can say this for my students, probably if you're taking a calculus class right now and you're in your beginning, just now starting integration, for the rest of the year, you're going to be using the power rule for antiderivatives. To use this rule, we need to see the exponent. X to the n is your exponent. You're going to add 1 to your exponent divided by the exponent plus 1. So instead of subtracting and multiplying, we're going to add 1 and then divide. Okay, or you can represent it like this, right? So in some textbooks, you got your base to the exponent plus 1 divided by the exponent plus 1. That's another way to illustrate it, I guess. But it's basically the same thing. You're adding 1 and then dividing, as opposed to subtracting 1 and then multiplying. So, but this is called the power rule for antiderivatives. Right? So to get your antiderivatives, whether we're doing indefinite integration or definite integration, we have to use the power rule. And virtually every day, the rest of the year, my classes are going to be using this almost on a daily basis. Now, a little example here. Let's do this one here. And this is real simple. We got x to the 3rd power here. Let's find the antiderivative. Right? So using the general power rule. Now, the exponent is 3. All right? So this will give us x to the 3rd power plus 1. Divided by 3 plus 1. Plus 1. Then this is adding 1 to your exponent and then divided by gives us x to the 4th power over 4 plus c. All right, so the antiderivative of x to the 3rd would be x to the 4th plus c. Now if you want to, you can write this like so. There's 1/4 x to the 4th plus your constant of integration. So if you want to, you can write it like this. It's pretty much the same thing. Okay, let's do another example. It's a couple really short examples here real quick. Okay, what about x to the 2/3 power? Now once again, 2/3 is your exponent. You're going to add 1 to your exponent divided by the exponent plus 1. So this would be x to the 2/3 plus 1. Now your exponent is a rational exponent, it's a fractional exponent. So 1 is the same thing as 3 over 3, so we'll write that as 3 over 3. 3 over 3 is the same thing as 1 divided by 2/3 plus 3 over 3. Now, to simplify this, 2/3 plus 3/3 gives us 5/3. So it'll be x to the 5/3 divided by 5/3, okay, plus our constant of integration. So we've got to remember now, always add the plus c. Right? If you leave that off, it's actually incorrect. So you've got to make sure you add the plus c on. Now also notice that we've got our answer, x to the 5/3 divided by 5/3 plus c. So what you end up with is dividing by a fraction. So when you divide by fractions, remember, we're going to multiply by the reciprocal of 5/3. So x to the 5/3 divided by 5/3 is actually equal to 3/5 x to the 5/3 plus our constant of integration. So kind of simplified a little bit. You don't want to leave that fraction really on the bottom of your that fraction, so like a complex fraction. So instead of dividing by 5/3, we're going to invert and multiply. That gives us 3/5 times x to the 5/3 power plus our constant of integration. I think we want to do another one here. Let's try this one here. Okay, x to the negative 1/3 power. And once again, we're going to take the x to the negative 1/3 plus 3 over 3 divided by negative 1/3 plus 3 over 3. Now adding the negative 1/3 plus the 3/3 gives us what? X to the 2/3 divided by 2/3 plus our constant of integration. Now once again, we're dividing by this fraction, so you're dividing by 2/3, so let's multiply by the reciprocal of 2/3. And this will simplify as 3/2 x to the 2/3 power plus our constant of integration. So the antiderivative of x to the negative 1/3 is 3/2 x to the 2/3 power plus c. So this will be the expression for our antiderivatives. Right. Let's take a look at the integrals of some of our trigonometric functions. Right. Now, just talking to my students in my calculus class, you know, we're going to have to they're going to have these memorized. Just like they memorize the derivatives of the trig functions, we're going to have to memorize the antiderivatives of the trig functions. So here's the first. The antiderivative of cosine x is sine x plus c. The derivative of sine x is cosine x, so the antiderivative of cosine x is sine x plus c. That's our first. Next, the antiderivative of sine x with respect to x is negative cosine x plus c. If you remember, the derivative of cosine is negative sine, right? Then the antiderivative of sine x is negative cosine x plus c. So that's our second trig integral you need to remember. Now the next one, the antiderivative of secant squared x dx equals tangent x plus c. So remember, the derivative of tangent is secant squared. Well, the antiderivative of secant squared is tangent x plus c. Number 4, the antiderivative of secant times tangent. A secant tangent is secant x plus c. And I guess if you remember from derivatives, the derivative of secant is secant tangent, so the antiderivative of secant tangent is secant x plus c. Number 5, the antiderivative of cosecant squared x is negative cotangent x plus c. And then the last one here we're going to look at is the antiderivative of negative cosecant x cotangent x is negative cosecant x plus c. So once again, there's 6 trig integrals, antiderivatives, that we need to have memorized. All right, so these you need to know. When you come across a trig problem, okay, you don't want to have to think about it. You need to be able to pretty much look at it and indicate your antiderivative immediately. So these we want to commit to memory. All right. Now let's look at another example or two. We'll do 1 or 2 examples of antiderivatives, and then we're going to finish this video up, and then we're going to start the next video. Right now, the next video has a whole bunch of examples. This is a couple of small examples. Now let's do the antiderivative of 3x. Now if you want to, you can pull the 3x out in front of your integral, but we really don't have to. So as you find the antiderivative, this will be 3 times. Now the antiderivative of x, this is x to the first power, so you're going to add 1 to your exponent. Gives you x to the second power divided by 2, plus your constant of integration. So instead of subtracting 1 and multiplying, we're going to add 1 to your exponent divided by the exponent plus 1. That's your antiderivative. Now let's simplify it a little bit. As you multiply 3 to this fraction, this will actually simplify as 3 over 2 x to the second power plus c. So you can write it like this. 3 times your fraction, that would be 3 over 2 x to the second power plus c. Okay, let's do another one. We'll just do 1 or 2 real simple examples. Okay, let's try this one here. So 1/2 x to the 1/2 power. Right, now as we, once again, as you multiply here, this will be 1/2 times. Now the antiderivative of x to the 1/2. Now you got to add 1 to your exponent, right? So remember, when you look at 1/2 plus 1 is actually 1/2 plus 2 over 2, okay, which is 3 over 2. So adding 1 to your exponent gives you x to the 3 over 2 divided by 3 over 2 plus c. Right, now we want to simplify this a little bit. Okay, you've got this fraction, right? Instead of dividing by 3 to the second power, we're going to multiply by the reciprocal of that fraction. So we end up now with 1/2 times 2/3 x to the 3/2 power plus c. Right, so you can see that step. Now what happens here, the 2's kind of cancel each other out, right? So those are going to cancel. And that leaves us with what? 1/3 x to the 3/2 power plus our constant of integration. Okay, let's take a look at example number 3. Let's try this one here. 1 over x to the 3rd power. Now, one thing with anti-differentiation, I said there's only the one major rule. That's the power rule. Okay, we need to see the exponent. There's no quotient rule to work with fractions. There's no product rule to work with multiplication. You got to go ahead and multiply, and then you got to use the power rule. So let's do 1 over x to the third. Now this is equivalent to x to the negative 3 dx. Right? Now we can use the general power rule for antiderivatives. Adding 1 to your exponent gives us x to the negative 3 plus 1 gives us negative 2, divided by negative 2 plus our constant of integration. Now, I'm going to pull that negative 2 off. This will be negative 1/2 x to the negative 2, okay, plus c, and man, we probably would not want to leave that negative exponent in here. So if you rewrite this without the negative exponent now, this would be negative 1 over 2x to the second power plus c. So if you write it without the negative exponent, this is what it would look like. Okay, and let's do one more. We'll do a little trig example here. Okay, the antiderivative of 2 sine x. So the antiderivative of 2 sine x. Now, as we indicate try to find our antiderivative, this will be 2 times the antiderivative of sine x. Now, remember the rules that we just looked at with our trig functions? The antiderivative of sine is negative cosine. So it will be negative cosine x plus our constant of integration. Right? And then as you multiply here, this is going to be negative 2 cosine x plus c. So that's just a couple of fairly simple examples that I can do here on the PowerPoint. For some more examples, you'll need to look at my next video. We'll do some more complicated examples. We're going to actually take a look at a couple of differential equations in the next video also. But that'll finish us up. Hopefully you found the my video here somewhat helpful.